So let's just start with. So I welcome all of you to the today's session, which is CEO Computer Architecture Short Notes, and in which I will be discussing everything important formulas, important definitions, and all regarding the subject computer architecture. So before that, let me introduce about myself. So my name is Deadlock. You can call me Deadlock. And I got All India 115 GATE Computer Science, and I am the alumni of IIT Bombay. So because of some security reasons, I can't unable to show my face and all. So that's why. But you can call me Deadlock. Okay, you can call me Deadlock. Now, let's just start with the prerequisite first. So we have seen, right? So this is the prerequisite. So we have two type of things in the computer entire computer architecture. Either we have to give answer in terms of time, or we have to give answer in terms of data. So if you have to give terms answer in terms of time, then if you have these units like kilo, mega, and giga. So if you have time, then kilo is 10 power 3, and if you want to represent it in data, then it will be 2 power 10. Okay, 2 power 10. So almost these two values are same. So 10 power 3 means 1000, and this will be 1024. So almost both are same. Okay, almost both the values are same. Similarly, one mega is 10 power 6, 1 giga is 10 power 9. And similarly for the data, it's 2 power 20 and 2 power 30. So this is important. Okay, this is important. You must know, or you must know this. You must know this. Because these things will come again and again. These things are coming in the questions again and again. So whenever you have to tell the things in terms of time, for this unit kilo, mega, and giga, use this particular values. And if you want to give the answer in terms of data, then use these values. Okay. Now, proceeding further. So we have seen three types of buses, right? We have three type of buses, like address bus. It is a unidirectional from CPU to memory, right? We have seen there is a CPU, there is something called a CPU, there is a memory, and there is a IO also. So the address bus, it is a unidirectional. Okay, it is a unidirectional because CPU generates the address, and it has to carry the address from CPU to memory. So this is the unidirectional. We have another bus which is data bus, that is bidirectional. And bidirectional means in both the ways, like from CPU to memory and memory to CPU, we can transfer the data. And we have another bus which is control bus. So it is partly bidirectional, which means it is also bidirectional, but individual line is unidirectional. So like individual line is unidirectional. So we have in the system, we have three type of buses. Okay, address bus, data bus, and control bus. Now we have seen this particular important formula. If the address bus has n bits, how many maximum addressable allocations, like locations, we can represent? We can represent 2 power n, right? 2 power n. If you have n bits, then we can represent 2 power n locations in memory, right? In memory. So if let's say this is the address bus. Okay, if this is the address bus, right? If this is the address bus, so you all of know, right, that there is a decoder here. There is a decoder here, and with the help of the decoder, you can represent all of. So if this is the address bus, and this is the n bits, you can represent 2 power n, right? 2 power n locations. Do you remember? Are you recalling this thing? Are you recalling this thing? Yes. So yeah. So if this is the CPU, right? Yeah. Now, same thing. So now, if let's say you have 32-bit data bus. So what the 32-bit data bus means? CPU can transfer 32 bits at once, right? CPU can transfer 32 bit at once. So if you have higher width, then higher throughput. So I have given example at one example, 8-lane road versus 32 lane road, right? Lane road. So similarly, so if you have a higher width, if you have a higher width, which means that more data can be transferred, right? More data can be transferred. So more data can be transferred, which have higher throughput, right? Which have higher throughput means higher throughput, which means that in 1 second we can get maximum data, right? We can get maximum data. So all these things we have seen in detail in our lecture notes, right? In our lecture we have seen in this detail. So important things only I have kept in the short notes. So now the next point is what does it mean if you have 32-bit architecture? So what does it mean? If you have 32-bit architecture, what does it mean? Which means that ALU is of 32 bits. Then MDI, which is also, so MDI means memory data register, which is 32 bits. And word size is also 32 bits, right? Word size also 32 bits. We have seen many questions related to this point also, right? That if you have 32-bit architecture, what does it mean? What does it mean? In what does it mean? CPU can process 32 bit at once. Are you remembering? Are you recalling what the 32-bit architecture means? CPU process 32 bits at once, right? At once. Yes or no? Yeah, at a time 32 bit can be processed. Yes. Now, next point. Next point is micro operation. So what is micro operation? We have seen it the smallest operation which CPU can execute in single step, right? This is the smallest operation. This is the smallest operation which a CPU can execute in a single step. In a single step, this is the smallest operation. And the time taken to execute one micro operation, that is called as CPU cycle time, right? CPU cycle time. So this is the definition of what is the micro operation and what is the time taken to execute one micro operation. That is your cycle time. That is your cycle time. Okay. The time taken is your cycle time. So this is the prerequisite that we have seen, right? This is the prerequisite we have seen. Now let me tell you. Then we have discussed in detail, right? We have discussed in detail about types of register. After the prerequisite, we have discussed the type of registers. So there are the CPU registers, right? We have seen. It is mainly divided based on the information which is stored, right? Information which is stored. So either okay, maybe I can. So it is divided in so divided with how information is stored, right? How information is stored. So there are two. So all the registers you can divide into two types, like data registers and information, and instruction registers, right? Instruction registers. How many of you are remembering this thing that we have divided into two, right? Data register and instruction register. So data registers means that those register will carry the data, and instruction register means those register will store the instruction. Yes or no? Now we have seen many types, right? We have seen many types. Like we have seen PC, program counter. PC, it stores the address of right? It stores the address of next instruction, next instruction to be performed, right? To perform. Address of next instruction to perform. Then we have seen instruction register. It stores the instruction, right? It stores instruction. Then we have seen memory address register, right? Memory address register. What it stores? It stores address, right? It stores address. Then we have seen MDI, so data register. We have seen, so it stores data, right? It stores data. Then we have seen flags, right? Then we have seen flags. So there are different type of flags, right? Zero flag, carry flag, overflow, and sign flag. Do you remember? Do you remember all this? We have seen the program status word, right? Program status word, different type of flags. And also we have seen accumulator, right? We have seen accumulator. So what the accumulator stores? Accumulator stores the result of ALU, right? Result of ALU it stores. Yes or no? So accumulator stores the result of ALU. Whatever is the result of ALU, that the accumulator store. Yeah, yeah, it stores the result. Yes. Now we have seen one important thing that ALU doesn't care, right? We have seen this important thing that ALU doesn't care that ALU doesn't care the type of data, right? Doesn't care the type of data, right? Whether it is signed, whether it is unsigned, whether it is represented in one complement, two complement, it doesn't care, right? It doesn't care. It just do the operation and it can ALU only does the operation and it can sets all these flags. Yes or no? We have seen this important thing, right? And there are the PYQs also with this topic. Yeah, yes. I remember, yes. So we have seen the different types of registers. Okay. And so these are the different types of registers which you have to remember. And now proceed further. We have seen the memory organization, right? We have seen the memory organization. We have seen the memory organization, right? Basics of memory organization. So we have seen this hierarchy, this memory hierarchy we have seen. Like in the level 0 we have CPU registers. In the level 1, then in the level 1 we have cache memory. Then in the level 2 we have main memory. So then in the level 3 we have magnetic disk, and then in the level 4 and 5 we have higher disk storage, and optical disk and magnetic tape and all. So all this thing we have seen. So if you go here, so see here in look into this particular arrow. So if you go this way, then what will happen? Increase in cost per bit. So here it is very costly, right? It is very costly. Then it is somewhat less costly, right? Somewhat less costly, and so on, right? And so on. And it is cheaper, right? These are the cheaper, because registers and all are fast, right? Registers, cache memory, all are fast, so that's why it is costly. Now the second thing we have seen, that it is faster, right? It is faster. And then if you go on, then it will be slower, right? And also one thing we have seen, that this is the faster, also it stores less data, right? It stores less data. Then if you go down, then here more data will be stored. Yes or no? More data will be stored, so less data stored. Yes, this is the hierarchy triangle we have seen. Remember? How many of you remember this? How many of you remember this? Yes. So now going further. So see, first see the byte addressable memory, right? Byte addressable memory. So if you have 256 KB byte, you have to represent like this way: 256K into 1 byte. And what does it mean? 256K into 1 byte means, which means 8 bits, right? 8 bits. Like, please remember this thing, that this is the standard representation of main memory. Standard representation, what is the representation? Number of cells into one cell capacity, right? Number of cells into one cell capacity. So in with this topic also, many questions, many pyqs we have seen. So here, see here it will be 256K cells, right? And each cell will store 8 bits. Each cell will store 8 bits. Yes. So this is the standard representation, like number of cells into one cell capacity. Okay, into one cell capacity. Now also we have seen that one cell equal to one memory location, right? We have seen this diagram. Like if this is your main memory, this is your main memory, right? This is one cell, this is one cell, this is another cell, and so on and so on. So this is one memory location, this is another, right? These are the memory locations. These are the memory locations. Yes or no? So one cell equal to one memory locations. Now, now we have seen, okay, we have seen then two types. Like the main memory is divided into, like main memory is classified into two types: byte addressable and word addressable. Right? Byte addressable and word addressable. Two types: byte and word addressable. And by default, memory is byte addressable. So byte addressable is by default, right? By default, byte addressable is memory is byte addressable. Yes or no? So now, what is the byte addressable? What is the byte addressable? Byte addressable means byte addressable. How many of you remember? So what is the byte addressable? One cell will have one byte, right? One cell contains one byte. And what is the word addressable? What is the word addressable? One cell contains one word. Yes or no? One cell contains one word. So this is the byte addressable and this is the word addressable. Like one cell will contain one byte and one cell will contain one word. Yes, I think everyone has given correct answer. So here in one addressable, right? In word addressable, one address contains one word. And what is the word size? What is the word size? Word size is equal to number of bits CPU processes in one go, right? Word size is same as. So if example, if it is given as 32-bit architecture, right? 32-bit architecture. What does it mean? One word equal to 32 bits. Yes, one word equal to 32 bits, and one cell will contain. So similarly, one cell will contain one word. So one cell will contain 32 bits. Yes, yes, clear, clear this thing. Yes, address bus also. Yes, yes, address bus also. So one cell equal to if it is a 32-bit architecture, then one word equal to 32 bits. And we know that in a word addressable, one address contain one word. So one cell will have one word and one cell will have 32 bits. Right? Now, if next point, if memory is given word addressable and word size is not given, see if sometimes word size is not given, then what we consider one word size equal to word size of CPU. So we are taking this, right? If word size is not given but this will be given 32-bit architecture, so that is the word size of CPU. So one word size equal to word size of CPU, right? So this example I have given. So this is the same thing which here it is mentioned, right? In this point it is mentioned. Now next point, what will be the address bits if you have 2 power n, right? If you have 2 power n locations, what is the address bits? How I have we have seen many questions, right? We have seen many questions regarding this. If you have address bits 2 power n, so what we have to do? We have to do, if you have 2 power n addresses, right? How to find the address bits? You have to do log base 2 and number of addresses, right? Number of addresses to get bits. So if you have 2 power n locations or addresses, tell me how many bits are needed. So n address bits, right? N address bits. What I have did, log base 2 power n. Yes, there are many questions we have seen in with this formula. We have seen many questions. Word size is the size of word size is the size of address bus, right? Address bus, because it is, See here also I have given. So 32-bit architecture, which means ALU is of 32 bits MDI. So MDI means, oh yeah, so MDI means data register. Yes, yes. So it is also 32 bits and word size equal to 32 bits. Yes, yes. So yeah, if CPU can process 32 bits as a one, right? CPU can process 32 bit as a one. What does it mean? You require address, you require data bus to be 32 bits to get that data from memory to CPU, right? Memory to CPU, right? I think many of you have confused in that in the lectures also. Like uh, many of you have confused that what to take, right? Like data bus and address bus. But you can, if you know this, like CPU can process 32 bit at once. What does it mean? So 32 bits, 32 bits data have to be come from memory to CPU. So that's why data bus is 32 bits. I remember that many of you did the mistake in this, yeah. But you can correct. You can correct now. You can correct now. Yeah, 32-bit data. Yes. So shall we proceed? Shall we proceed? Shall we proceed further? Okay. Yeah. So now we will see. See. Now we will see. So the decoder is used to access the specific cell using the address, right? So this I have already shown here. I have already shown here. See, if you have CPU, then if this is the address, if this is the address bus, then the decoder you needed, right? Decoder is needed to select one of this location, right? To select one of the locations, like 2 power n locations. Yes, decoder is needed. So the same thing is written here, that the decoder is used to access the specific cell using the address, right? Using the address, like using the address bits. Now we have seen that there is a two types of RAM. There is two type of RAM: static RAM, SM, and dynamic RAM, which is DRAM. Now SM doesn't require refresh operations as it is made up of flip-flops, while DRAM requires the refresh operation as it is made up of capacitors, which stores the data in form of charges. Right? Capacitor will store the data in form of charges, and it requires the periodic refreshing. Right? It requires the periodic refreshing. So your SM will be okay. So cache memory is made up of SM, right? And main memory is made up of DM. Main memory is made up of DM, right? We have seen the one table also, right? Like what is the difference between static RAM and DM? But that table is not important. You just know the definition, like what the SM is and what the DM does, right? And then there is a concept of refreshing that is important, like some of the pyqs, like I think 3 4 pyqs are there in the refreshing topic. So we have seen that in one refresh operation, right? In one refresh operation, what we have seen, one entire rows of shell are refreshed. In one refresh, one entire row of shells are refreshed. So one chip refresh time, what is one chip refresh time? Number of rows into refresh operation time, yes or no? One chip refresh time, one entire chip, right? We have seen this. Uh, See, if we have this chip, right? If this is the chip and this is the rows of cell, right? So this is the cell, this is the cell, right? This is one row, this is one row. Like, and similarly, all the rows have these cells, right? If this is one DM chip, right? This is the DM chip. Now what it is given? In one refresh operation, what happens? In one refresh operation, one entire rows of cells are refreshed. So in one refresh, okay, maybe I can add here. So this is the address bit. So in one refresh, what will happen? One entire row of cells will be refreshed, right? Will refreshed. Now if you want to refresh this entire chip, right? If you want to refresh entire chip, so what is the total time? What is the total time? So number of rows, right? We have to refresh each row. We have to refresh this row, this row, this row, this row, and each row. So number of rows into one refresh time. Yes or no? One refresh time. Yes or no? Right. So the same thing how is written here. So in a one refresh operation, one entire rows of cells are refreshed, and so one chip refresh time will be number of rows into refresh operation time. Yes. And also we have seen this thing that if you have many chips, right? If you have many chips, like this is the chip one, this is the chip two, this is chip one, chip two, and so on, many chips. So all the chips are refreshed parallelly. Okay, all the chips are refreshed parallelly. So one chip refresh time is equal to n chip refresh time. We have seen it. One chip refresh time is same as n chip refresh time, because all the all the cells are refreshed parallelly, right? All the chips will be refreshed parallelly. Yes or no? And then we have seen this formula, like in one refresh period. See, we have also seen this, that if this is your okay, if this is your one refresh period, one refresh period. So here what happens? For some unit of time, right? For some unit of time, it is divided into two portion. Like read can happen or refresh can happen, right? Refresh can anything, right? It is divided if refresh happens. So that is the one refresh period. So that's what here written, that in one refresh period have X amount of read and write and Y amount of refresh. So what is the percentage of time? So what they are saying, that X amount of read and write and Y amount of refresh. So percentage time for refresh will be how much, will be how much, how much time refreshing is happens, y times y. So y divided by what is total time, x plus y, right? X plus y. So x plus y into 100%. Yes, this is simple, right? This is simple, yeah. Y divided by x plus y into 100. So that's what here it is written, that percentage of time for refresh will be y divided by x plus y into 100. Yes or no? Yes or no? Tell me. Now we have seen the memory interfacing, right? We have seen the expansion, right? The expansion topic we have seen. So in multiple chip memory, one decode output selects one entire horizontal arrangement. So yeah, so we have seen this thing, right? We have seen two type of arrangement, like horizontal arrangement and vertical arrangement. So see, if you require the address is more, right? If you require more address, what you do? You do vertical arrangement. And if you require the data, what you do? You do horizontal arrangement. Do you call this thing? If you require more address, what you do? You stack the chips into vertically, right? You stack the chips into vertically. But if you require more data, right? If you require more data, what you do in horizontal? You will put here like this way. Like horizontally you put the chips. Horizontally you put the chips. So so that's the thing. If you require the address more than vertical arrangement, right? Because here you will get many addresses. And if you require the data more, then like vertically you will, like horizontally you will get more data, right? See, like in this way, right? In this way. So that's the thing here also written, that in a multiple chip memory, one decode output selects one entire horizontal arrangement, right? You know, right? If you have horizontal, and if our decoder, right? So you know, right? Here the decoder will be required for one address selection. So if decoder have select this particular address, so this entire things will be given, right? So it selects one entire horizontal arrangement, right? So this data also given, this data and this data also given. Yes or no? We have seen it. Yeah, horizontal increase the capacity of the cell, and vertical increase the number of cells. Yes. So if you require the address and data more, right? If you require both the thing, if you require both the things, then what you do? You do hybrid arrangement, right? Hybrid arrangement. So what the hybrid means? It is the combination of both vertical and horizontal. Yes or no? So this is the expansion topic we have seen, right? Memory expansion. Memory expansion, right? Now the next concept is little Indian and big Indian. So first of all, when this concept will be applied. So if our data is of multiple bytes, if the data is of multiple bytes, then only there are two ways to store, right? There are two ways to store that little Indian and big Indian, little Indian and big Indian. So if your data is of multiple bytes, then you have two ways, little Indian and big Indian. So now what the little Indian means? Little Indian means start with the little end, right? I have told L and L. Start with little end or LSB, right? LLL, little end or LSB. You have to start with little end. So if you have multi-byte of data, if you have this multi-byte of data, right? And this is your LSB, this is your MSB. So you have to start with LSB, little end, in little Indian. So if you have, let's say 01, 02, 03, and 04, right? So I am erasing this thing. So how it will store? How it will store? Can someone tell how it will store? So if you have two, right? Like two ways, right? Two ways. So this is the memory. This is the memory. Let's say this is the starting address 0001, 02, and 03. Similarly, 0001, 02, and 03. So what happens in case of little Indian? So this is the case of little Indian, and this is the case of big Indian. So what happens in little Indian? We start with the little end, yes or no? We start with the little end or LSB. So 04 will store here, then 03 will be here, right? We have to go like this way, and we have to store in start, we have to start with the little end. So 04 will be here, 03, then 02, and 01. Yes? And similarly for big Indian, what happens in the big Indian? What happens in the big Indian? Start with the big end. Let's start with the big end or MSB. So this is the MSB. So 01 will store here. So like this way, right? 01, 02, 03, and 04. Yes or no? So this way the data will be stored, right? Like there are two ways to store the data, right? There are two ways to store little and big Indian. Now, one important note, if you recall, one important note I have given, very important note, right? Very important note I have given, that engineerness comes into picture only when you have multiple bytes of data, right? When you have multi data, right? Only when you have multiple bytes of data, then only engineerness will comes into the picture. Otherwise, it won't come into the picture. Yes. Otherwise it won't come into the picture. And we have seen this important thing. It only applies to primitive data items, like not to stock or string, not to a stock or string, right? We have seen the in detail, we have seen in detail. I hope you all remember that it is not applied to a stock and string. Yes. So this is all about the two types of endianness, like two ways to store the data, right? Now we proceed further. So then we have seen something called as instructions and addressing modes, right? We have seen in detail what is the instructions, what are the different addressing modes. So what is the instruction? So it is a binary pattern that tells the CPU what operation to perform and on which data. Yes. So you have something called as instruction register, right? Instruction register stores the instruction, like instruction it will store, right? Instruction it will store, and it is the binary pattern, because in the computer everything will be stored in terms of zeros and ones, right? Zeros, one, zero, one, and on, right? So it tells the CPU what operation to perform and on which data. So how we know, how we comes to know? Can anyone tell me? From the instruction register, from the instruction register, how the CPU can get to know what operation to perform? How CPU gets to know? Yes, yes. So, see, your entire instruction will be divided into two types, like opcode and operand, right? Opcode and operand. So opcode will tell which opcode. Okay, so here I'm writing opcode will tell which operation to perform, which operation to perform, and what the operand will tell on which item, right? On which item to perform the operation, on which item to perform it, on which data item. Now, now, maybe I can use this color. Yeah. So opcode. Okay. So from the opcode, what happens? What happens? There is something called as decoder, right? Decoder. Like here we have decoder. Like, who tells the CPU first of all? If someone can ask who tells, then the answer is control unit. Yes or no? Control unit does the decoding and all. Control unit does the decoding and all. CU. Control unit does all the things. So in the inside the control unit, there is something called as decoder. And if we give this, if we give this, okay, if we give this opcode, then it will tell which operation to perform. If you have add, if you have sub, if you have move, and so on, right? If you have all the different type of operations, then the decoder will tell, that which operation to perform, right? Which operation. These are the different operations. Yes. So it is instruction. This is your instruction format, right? This is the instruction format. It is divided into opcode and operand. So opcode will be operations like add, sub, load, and so on. Yes. Now, if the opcode is of n bits, how many number of unique operations a CPU can perform? How many number of different unique operations a CPU can perform? If the opcode have n bits, then 2 power n, yeah, 2 power n. And then we have seen ISA means instruction set architecture, right? ISA means instruction set architecture, and what the it stores, it contains the set of all types of instruction which is supported by CPU, right? All the different type of instructions which are supported by the CPU, all the different type of instruction which are supported by the CPU. Yes or no? Then we have seen, then what is the operand? Operand. Then what is the operand? Operand will be either the data or address. Yes? Are you recalling what the operand? Operand will be either data or address. But how we can know? How we can know that whether it is data or whether it is address? Then who comes into the picture? Addressing modes, right? Addressing modes. Addressing modes will tell us how to locate the operand. Yes, how to locate the operand, or we will get operand. How we will get the operand? Yes, the addressing modes will tell us. Addressing mode will tell us. And we have also seen that the instruction execution, like to execute the instruction, 3 cycles are needed. Like first you have to fetch, then you have to decode, and then you have to execute. First you have to fetch it, right? We have seen this thing, like from the PC it will be go into MAR. From the MAR there is a decoder, from that you select one of the address, then you go to the CPU, right? Then from the CPU, if we then you CPU, all the data will come into MBR with the help of data bus. And if you have instruction, it will be stored in IR, right? Instruction register, if it is instruction, right? And from the instruction we will decode, right? From the instruction we will decode, and we get to know that which instruction will be performed. So this entire things is your fetch cycle, right? Fetch, this thing is your decode, and based on which operation to perform, that will be your execute cycle. Yes, the entire flow. How many of you remember the entire flow? Right? From PC to MAR to decoder to CPU, then coming back to MBR, then IR, and then with the help, when you go like this, here you will get the instructions, right? Here you will get the instruction. So I am using this thing. Okay. So we have seen the instruction execution. Now the instructions is divided into two types, like variable length instruction and fixed length instruction. So in a variable length instruction, you have a fixed length opcode, and if you have fixed length, right? What is the fixed length? Fixed length means each and every instruction is fixed, right? Each and every instruction is fixed. So there you have variable length opcoded, and you know it that fixed length instruction is used in RISC. It is used in RISC. We will see the difference between RISC and CISC in a couple of minutes. And variable length instruction is used in CISC, and we have seen that in the fixed length instruction, because it is fixed length, right? Because it is fixed length, what it will happen? What happens in a fixed length? Some of the bits are not used, right? Some of the bits are not used because it is the fixed length. Like we have seen zero address mode, right? Then we have seen one address, we have seen two address. Yes or no? Here everything will be fixed. Here everything will be fixed length instruction. So what we can do, we have seen the expanding opcode technique, right? We have seen this technique, expanding opcode technique. We have seen, and and I have told that I have explained two ways, like two different methods, and then we have solved many questions with the help of method to it, like the simple method. What you have to do? Number of instructions into how many combinations, right? Plus number of instructions into how many combinations, and it should be less than it should be less than how many different embeddings, like how many different combinations we can get. Yes, we have seen this simple formula, like simple way to represent. Yes or no? How many of you recall this method to simple way? How many recalls the simple way? Yes. So here we are adding the number of instruction, let's say in one address mode, and then here we are selecting how many combinations we can generate. Similarly, here we are adding number of instruction in one address, and so on, which is how it based on the question, right? It will be given in the question. And what here we are writing, let's say if your instruction is 32 bits, so here we are writing 2 power 32, right? 2 power 32, and then we solve what was given. I think we many questions are coming, and we have seen the simple way to solve. Yes, pyqs, there are many pyqs with this topic, and you can do quickly, very quickly. You can do very quickly. Now then, we will see the type of instruction. So different type of instruction, like data transfer instructions, right? Data transfer instructions. So move, load, store, and all. Then arithmetic. So add, sub, mul, and all, right? Division, increment, decrement. These are the arithmetic operations. Then logical operations like and, or, XOR, not, and shift. Right? We have seen shift, logical shift, and arithmetic shift. Arithmetic shift. Yes or no? And then branch, different type of instructions are branch or control. So jump, then branch if equal, branch if not equal, and call and return. Right? These are the control instructions. These are the transfer instruction. This is the arithmetic. These are the logical. Right? So they are the different type of instructions. How many of you recall? How many of you recall this thing? Yes. So now we'll proceed. We will proceed further. So then we have seen in detail. We have seen in detail the different type of addressing modes. What are the different type of addressing modes? So the addressing mode. What is the addressing mode? It will tell how the effective address. Okay. It will tell how the effective address. Effective address, which means address of operand. Yes. How the effective address or operand address or target address of operand is calculated. Yes. It will tell how the effective address will be calculated. Now addressing mode, the different modes is the formula for effective address. Okay, this is the addressing mode. This is the addressing mode. It is a formula for effective address, which means it will tell the different ways. It will tell, it will, what it will tell. Yeah, it will tell from where to pick the operand. Yes. So it will tell how the effective address or how the target address of operand is calculated. So first is immediate. First is immediate addressing mode. Immediate addressing mode, which means see here, move I1 comma hash phi, right? Move I1 comma hash phi. So hash phi means this is the operand, right? Operand will be operand equal to phi, right? Operand equal to phi. I think before that we have also seen, yeah, here. Okay, we have first seen implicit, yeah. So that's what I was saying, whether I have written or not. But I have written here at the end. Yeah, so we'll discuss. We'll discuss. Right now, next addressing mode is direct addressing mode. What is the direct addressing mode? Effective address, which means address of the operand, will be address in the instruction. Like in the instruction, in the instruction itself. If this is the instruction, right? This will be your address. This will be the address. Okay. Okay. So if you have move I1 comma 1000, so if you go to 1000 location, right? In the memory, mm, yeah, if you go to 1000 location, if you go to 1000 location, then you will get the operand. Here you will get the operand. Yes. So you have to visit the main memory one time. One time you have to visit, right? One time you have to visit. Now, next is indirect. Next is indirect addressing mode. So effective address will be memory of address. Okay. Effective address will be memory of address. So it, for example, move I1 comma 1000. So if you have opcode and if you have this address, right? This is the opcode and this is the operand, right? Operand. So what you do, you go to memory location one time, right? One time. Then here, see here you will get the effective address. Here you will get the effective address. Effective address, which means address of the operand. Here you will get the address of the operand. Now whatever you will get here, if you go to that location, let's say that location is present here, and then you will get here operand, right? You will get the operand. Yes or no? Yes or no? So here we have to go two time, right? Two time we have to visit the main memory. Two time visit the main memory. Yes. Here you have to one time you have to visit. One time visit. Yes. See here we just going one time, but here we are accessing two time. Right. That's why I have written we are accessing two time. First time we are accessing to get the address of operand, and then we are going at that address to get the operand. Yes. Yeah. Pointer implementation. Yes. Here pointer will be implemented. Pointer implementation. Yes, pointer implementation. Immediate. How many of you remember immediate? Immediate, which means variable storing, right? Variable storing the data in the variable, right? Storing the data in the variable, storing the data in the variable. Then next is, now we'll proceed further. So the next is register addressing. What is the register addressing? The operand is present in the register. Like example is move I1 comma I2. So here only if you go to the I1 register, you will get the operand. You will get operand. Yes. So that is the register addressing. Register addressing. Now now we'll see what is the register indirect. What is the register indirect addressing? So effective address will be content of R2. Right? What does it mean? What does it mean? See, example move I1 comma R2. So if you have like this, right? If you have R2, right? So what you do? What you do? You in the R2 right? In the R2, what you will get? What you will get? Effective address, right? Contents of R2 will be effective address. So in the R2 you will get the address of operand. In the R2 you will get address of operand. So you go to that address, right? You go to that particular address. You go to that particular address and you will get the operand, right? So here also one time visit, one time visit. Yes. So this is the register indirect addressing. Register indirect addressing. And then we have seen this three type of displacement based addressing, right? Displacement based addressing modes. How many of you recall this? We have seen three type of displacement based addressing modes. Displacement based addressing modes we have seen. So based on the displacement, right? Based on the displacement, like based on the types of register, right? Based on the type of register, right? There are three types. There are three types. So see, in the index addressing, effective address will be base address plus index register, right? Plus index register. So example this. What does it mean? A plus. So A is your address and R2, right? Index register. Index register. Similarly, base or displacement addressing. So what does it mean? Here you have base register, right? You have here instead of index register, you have base register. Yes or no? Plus offset, plus offset. Yes, plus offset. And then you have relative addressing, which is PC relative. So effective address will be PC, right? Instead of index register, instead of base register, you have PC register, right? PC register plus offset, plus offset. How many of you recall this thing? We have seen some of the questions also, right? Related to PC addressing, PC relative. And I told that it is used for index addressing. It is used for implementation of array, right? Implementation of array. And it is used for uh, changing the position at like changing base addressing, right? Base addressing is used for changing the code, right? Changing the code, like the location of the code, changing the location of the code. There are the PYQs also, right? Some direct PYQs, yes, relocatable code, yes, relocatable code we have seen. So yeah, so this is all about the displacement based addressing mode. Yes, displacement based addressing mode. Now we have seen one type of addressing, which is auto increment and auto decrement, right? Auto increment and auto decrement. So what it do? It automatically does plus plus and minus minus. Yes, it automatically does plus plus and minus minus. Remember, remember PC. Remember PC. Yeah. So auto increment and auto decrement is used in the loops, right? In the loops we generally have to do plus plus and minus minus, right? We generally have to do plus plus and minus minus. So here same thing, the same thing. PC will be incremented or decremented. Yes, PC will be incremented or decremented. Now next is implied or implicit addressing, right? Implied or implicit addressing. So what does it mean? Operand is implicit. Operand is implicit. So for example, if you have clear, this is the clear instruction. Clear A, clear A. So what does it mean? So the accumulator is implicit here. Accumulator is implicit. So you have to clear the accumulator. It's like implicit addressing means they won't give much information, but those things like where to get the operand will be implicit. Yes, it will be implicit. Yeah, we have seen the in the stack based. We have seen push. We have seen pop. Right. So see here, uh, which is used in the bands, which is used in the bands. So PC relative, right? PC relative. PC relative is used for bouncing, right? For jumping, for jumping. And used in as will be index or base, right? Index or base. Like the base addressing also can be used for the array implementation. You just have to because you just have to change the base register, right? You just have to change the base register. So this I think is all about types of addressing modes. Okay, different type of addressing modes. Right? There are many PYQs in with this topic, like direct. Some are the direct. Like I think every PYQs are direct PYQs, like based on the definition. Some, let's say some two or three PYQs are only some indirect PYQs, but mostly if you know the definition, right? If you know the definition, you can easily solve. Yes or no? You can easily solve. You can easily solve them. Yeah, we have solved also. So now we will see difference between risk and sys. Here also direct PYQs are coming. If you know the definition and if you know the concept, right? If you know what is risk, what is sys, you can easily solve. So risk means reduced instruction set computer, and sys means complex instruction set computer. Yeah. So what is used currently? So in our day-to-day life, risk is used. In our day-to-day life, mostly risk is used mostly. Okay, mostly. Now see these two diagrams. Maybe I can go with first this. Let's see this. Here in the risk, right? Here in the risk, simple instructions are used, right? In the sys complex instruction are used. In the risk, you have fixed length instruction. In the sys, you have variable length instruction. Yes. Can someone tell me what is the job of risk and sys? What is the job of risk and sys? What is the job of risk and sys? What is the main goal of risk and sys? So if you recall, we have discussed that risk main job was to uh, time, right? Time to execute in less time, to execute, okay, to execute, to save time, basically to save time. I'm writing to save time, right? To save time. And what is the job of sys? To save memory, right? To save memory. Yes, we have discussed in detail, like what is the uh, like we have taken one example, and then we have seen the things like in the sys, just the entire program will be solved in two or three instructions. But if you use risk, there will be many instructions, right? Many instructions. In the lectures we have seen in detail. Now here, see here, simple and limited addressing modes, right? Simple instruction. But here we have complex addressing modes. Here less number of instruction. Here more number of instructions. More number of instruction, right? Because complex instruction you have to store complex instruction. Here it is easy to implement using hardwired control unit, but it is difficult to implement using hardwired control unit because it is simple. Here, one instruction will take one cycle. Here, multiple cycle per instruction, right? Multiple cycle per instruction. Here, mostly register to register arithmetic operation. But here register to memory or memory to registers. Here more number of registers are used, and here less number of registers are used. Right? So this is the simple difference between risk and sys. Like in the risk, many things will be simple. Right? You have a simple instruction, you have simple addressing mode. Like one instruction, because it is simple, so one instruction will take one cycle and more number of registers. Right? So here its goal is to save time, and here its goal is to save memory. To save memory, you have complex instruction, you have more number of like different instructions, right? Because it is complex. And here variable length, because complex instruction used, and it is difficult to implement. And because see, here it is variable length instruction and complex instruction, it takes multiple cycles, right? Multiple cycles to execute, because it says job is not to save the time, right? Its job is to save the memory. Yes or no? How many of you got this risk and says? Are you able to recall? Are you able to recall? Yes. So now I think this is the same thing. This is the same thing. This picture I have taken from my IIC, right? From my IIC. So here register to register instruction, memory to memory, right? It execute in one cycle, and here many cycles it will take. It minimizes the execution time, it minimizes the size of program. It is not hardware heavy, it is hardware heavy. It is assembly programmer life is hard, right? Because they have to write the simple code. But here assembly programmers life is easy because complex instruction, right? We have seen that just in couple of two three simple instructions, like two three complex instruction, you can easily solve the big program. So here assembly programmer life is easy. Here more registers, here less registers. Here pipelining is easy, but here pipelining is hard. Yes. So this is the detailed difference between both risk and sys. This is the detailed difference between risk and sys. Now we proceed. Okay. Okay. So now we proceed further. Yeah, so pipelining will be easy here. Pipelining will be easy here, and pipelining is hard here, because here each thing will be executed in one clock cycle, and here we don't have to do many things, right? Here see, here it's easy to implement also, and here everything is fixed length instruction. So here pipelining will be easy in the risk, and we also seen risk pipelining, right? We have seen risk pipeline, like your five stage pipeline. That's the your classical five stage pipeline, risk pipeline. So that's the thing. And here pipelining is hard because each stage you have to do many things. You in each stage you have to do many things. Like complex instructions are there. So each stage will take time also, right? Based on the instruction. We don't know, because here instructions are complex. So we don't know that which instruction you will use. So based on that, the time also will take more and stuff like that. So in the CISC, pipelining is hard, right? In the pipelining will be hard. Okay, okay. Now, now we see in detail, right? Then we have seen detail about the disk, right? We have seen each and every detail. Right? How many of you remember this diagram? Right? We have something called as ARM assembly. Right? If this is the ARM assembly, right? This is the ARM assembly. There are the reader heads, right? This is the reader heads, and we have the cylinder. Sorry for the if the diagram is not somewhat proper. Okay, but I hope you are getting. So these are the cylinders, right? These are the reader heads, right? These are the radiate head. And the disk is constantly rotating, right? The disk is constantly rotating with the help of something called a spindle, right? Right, this is the spindle. Remember, remember the spindle, because the disk is keeps on rotating, right? Yeah, the disk is keeps on rotating. So with the help of spindle, it can rotate. There is a arm assembly. There is a radiate head, and uh, here, each particular platter, right? This is the platter. These are the platters, right? Each platter have two surfaces, like front and back, right? Like this is the front, then this is the back, so two surfaces. Each surface, each surface, right? Each surface will be divided into tracks, right? There is tracks, like it is divided into tracks. Then each tracks will be divided into sectors, right? Each tracks will be divided into sectors. Each is divided on every surface at a time. One head gets enabled. Yes. So that is reader head. Yes. So now, if you want to find what is the disk capacity, so 2 into number of platters will be your surfaces, right? Total number of surfaces. Total number of surfaces. Now, per surface how many tag into per surface how many tag? Yes. Per surface how many tag into per tag how many sectors, and one sector capacity, right? Each sector have capacity, right? So one sector capacity, one sector capacity. Right. So if you have this particular, if you have this tag, right? If this is the tag, right? Okay, if this is the tag, your each and every tag will be divided into sectors, right? Into sectors. So this is the sector, this is the sector. Yes. Remember this thing. Are you recalling? Tag, then sectors, sector capacity, right? So your tag is one entire tag is circular path, right? One entire circular path. Your sector is the smallest chunk. And what is the cylinder? What is the cylinder? What is the cylinder? Same radius tag, right? Same radius tags, right? So here, mm, okay, let me do with this. So if you have like you have many tags, right? You have many tags, many tags. But now, right? So you have this many tags across the platters, right? Across the platters you have many tags. But now if you pick this particular, if you pick this same radius tag, right? Same radius tag. So that is the cylinder, right? That is the cylinder. So see, this is the cylinder, right? These are the cylinders, right? Same radius tag. So the cylinder will be, what is the cylinder? Same radius tags across all the platters, across all the surfaces. Okay, across all the surfaces. Yes, yes or no? Tell me, yes or no? Cylinder. Cylinder will be same radius tags, right? Same radius tag. Now, see, each surface has one radiate head, and at a time only one can be active, right? At a time only one can be active. So each surface, see here also I have written 1, 2, 3, 4, 5, 6, right? There are the six radiate head, and at a time only one can be active, right? At a time only one is active. At a time only one can be active. So now next point is number of surfaces will be 2 into number of platters, right? So this we know. Now sector of tag will be disk sector, right? So what is the sector? It is also called as disk sector, right? It is also called as disk sector, and I have told that it is the smallest unit. It is the smallest unit which is addressable, right? Smallest unit which is addressable. Yes, yes, smallest unit which is addressable. So each sector will have address. Maybe if there is point, yeah, there is no point, but here you can add it. You can add one point here also. That each each sector have addresses. Each sector have addresses because each sector have address because each sector is addressable, right? Each sector is addressable. Yeah, I think here I have written sector is the smallest addressable unit which can be read or written at a once, right? Which can be read or written at a once. Now, what is the disk access time? What is the disk access time? So we have seen this formula, right? How to access the disk. So we have disk access time. So it is seek time plus rotational latency plus one sector transfer time, right? So what is the seek time? First you go to the particular tag. Yes. First you go to the particular tag. Yes. So that is your seek time. Then based on the rotation, you go to the particular tag. Maybe I can add particular tag, right? Then you go to the particular sector, that particular sector. Then once you go to the particular sector, what you can do? You can transfer the one entire sector. So one sector transfer time, yes, one sector transfer time, plus other delays. Other delays take zero if nothing mentioned in the question, right? Plus other delays. But if it is mentioned in the question, you can take it. But if it is not mentioned, then zero, right? Then take it as zero. Yes. Then what is the average rotation latency? How to find average rotation latency? So rotation time divided by 2. So here we had average rotation latency, right? We have seen example, right? Example, we have seen, let's say 200 RPM, we have seen, right? So in 60, in a 1 minute, right? 1 minute or 60 seconds, 2000 revolution, right? 2000 revolution, because rotation per minute. So one revolution will take how much time, right? And then we divide it by 2 to get the to get the average rotation latency. Remember how many of you recall this? Then we have one sector transfer time, right? One sector transfer time. So one sector transfer time will be rotation time divided by sectors per tech, right? Rotation time divided by sectors per tech. Most probably one sector transfer time if it is given, and if it is not given, you can you can find with the help of this formula. Yes, because we know that in a one rotation, in one rotation, what happens? Entire tag will be transferred. Right? We have seen this. Entire track will be transferred. Right? So one rotation you can find with the rotation time like this way, and then you can divide with the total number of sectors per tag. Got it? Got it? This thing. Got it? This point. One sector transfer time. Yeah. Okay, and then see, we use the concept of cylinder. So now next point, we use the concept of cylinder to store the file so that the seek time will be required only once, right? Seek time will be required only once. So we have seen that how our data will be stored. Are you able to recall how our data will be stored? First it will store based on each tag, right? Let's say this tag, then this tag, then this tag. Then we change the tag, like based on the cylinder wise, right? Cylinder wise, our data will be stored. Then we use this tag, then this tag, then this tag. So same way, like based on the cylinder to cylinder, our data will be stored, right? We have seen in detail, very detail. Like yeah, in cylinder, based on the cylinders, cylinder to cylinder, our data will be stored. Now, if someone can ask what is the number of cylinders, so number of cylinder will be number of tags per surface, right? Because if you have this surface, right? If you if this is one surface, right? One surface. In one surface you have one, two, three. In one surface you have three tags. So three cylinders you can form, right? Three cylinders you can form. Yes. So number of cylinders will be number of tags per surface. So I think this point is pretty much clear to you all. Right? Now next point. Now see. Now see. If you store, now we have seen this two. Now this we have seen this two formulas, and here some PYQs are also there, right? Some PYQs are also there. So if you store your file, right, sequentially, if you store the file, right, and if you have n sectors, then what is the total time? So seek time plus rotation latency plus n sector transfer time, right, plus n sector transfer time. But if you store randomly, randomly store n sector transfer time, right? If you store randomly, so n times we don't know randomly, right? Randomly, like each and everything will be randomly, and you have to transfer n sectors. So n time you required seek, right? N time you required seek, then rotation latency and one sector transfer time. Yes or no? Yes or no? Yes. Every time we'll need seek and rotation. Yes. Okay. So till now everything is clear. Everything is clear. Till now everything you got. Are you able to get it? Yes. Okay. So now we have seen something called as disk addressing, right? We have seen something called as disk addressing. So disk addressing, we have two types of addressing. First is CHS, right? CHS addressing, or LBA, right? LBA addressing, right? And what is the LBA addressing? LBA addressing, which means particular address at some one value will be given, one value will be given. Yes. So it is divided into CHS and LBA. Okay. So what is CHS? C means cylinder number, H means surface number, and S means sector number. Now we have seen it. So what is the sector number for given address? Okay. So if you have given this address, what is the sector number for it? So this is the CHS to LBA conversion, right? LBA conversion. So right, LBA conversion. So it will be C into sectors per cylinder plus H into sectors per track plus S, right? We have seen it. What is this C? What is this C? What is this C? How many cylinders have passed, right? How many cylinders have passed, plus H into how many, plus H means, right, we have, how many of you recall that for the zero based indexing, right? if we have if we have, let's say, 0 0. Okay. So let's say, for example, if you have 2 3 4, right? If you have 2 3 4, how to convert to LBA? So what 2 means? 2 means two cylinders have passed, right? Two cylinder passed. So 2 into how many sectors passed, right? So that's why we have to add sectors per cylinder plus. Now we are at the particular sector, right? Now we are at the particular cylinder. So at particular cylinder, see particular cylinder, which track, now we will see which surface, right? We will see which surface. So H means surface number, right? H means surface number. So three surface in a one cylinder, three surface to pass, right? Three surface. So you know, right, that in a cylinder one surface will have one track. Yes or no? In a cylinder one surface will have one track. So H into sectors per track, right? Here we are adding sectors per track. Now we are at the particular track. Yes, we are at the particular track. Now S means how many sectors to pass, right? How many sectors to pass. So this is in the zero based indexing, right? Zero based indexing. If you have one based indexing, then I have told that you have to do -1, like C -1, then H -1. Yes. And based on, if something will be changed in the question, you can take care. Right? You can take care. If it is given that it two based indexing, let's say two based indexing, but I think they won't give, because we have seen many PYQs that most probably, yeah, then -2, but most probably zero based indexing only is given in the PYQs. Right? Now this is the conversion from LBA to LBA to CHS, right? LBA to CHS. This is the conversion. This is the conversion. Right? I think I will add here. So how to convert? How to convert? You have to start with LBA, right? You have to start with LBA. Now you have to divide with the C, right? You have to divide with the C. Whatever you get, whatever the remainder you get, right? So this is the remainder. Mm, maybe yeah. Here you have to okay. Here you have to start with NC, right? You have to start with NC. Yes. So what is NC? We have seen that. We have seen that. C. Okay. NC means sectors. Okay. Maybe I can add here so that it. Yeah. NC will be sectors per cylinder. Right. Sectors per cylinder. Okay. NH will be sectors per tech. Sectors per tech. Yes. So see here we have to do reverse process, right? We have to do reverse process. So this is your uh, this is your NC, right? This is your NC. This is your NH, right? This is your NH, right? And this is your S, right? So whatever. But see here you are doing multiplication, right? You are doing multiplication. So you have to divide. You have to divide to get the CHS, right? So that's why we are dividing. So divide with the NC, whatever the remainder you will get, that is your C. Then you divide with NH, okay? Whatever the remainder, okay, whatever the remainder you will get, that is your H, right? That is your H. And whatever last you will get, that is your S, okay? That is your S. Yes, we have seen this, yes? Remember? Yes. So yeah, this is yeah. If you look into this formula, you can look it, but you have to remember all this. Instead this is pretty much straightforward. Eh? You don't have to mug up anything. Like it's the pretty much conceptual. So yeah, so cylinder is set of tags at same radius on all the surface. We have seen this. Seek time we have seen movement between the cylinders, not the tag. Yeah. Now next topic, like next PYQs, will be based on the disk scheduling. Right? We have the disk scheduling is used to have minimum seek time. Right? We have seen that if multiple requests come, right? Multiple requests come, how the scheduling will happen, how the like which request you have to pick, which request to pick, right? So for that disk schedulings are used, right? So for that disk schedulings are used. uh, okay, and we have seen that here your request will be cylinder number, right? There are cylinder 1, cylinder 2, and so on. Like different request of cylinders will come, right? Different requests. Now which to pick. So for that disk scheduling used, right? Disk algorithms. So we have seen FCFS, SSTF, scan, C-scan, look, and C-look. FCFS is first come first serve, right? Whichever is first, you have to you have to execute it, right? First come first serve. तुम पहला तो मैं पहला, तुम पहला तो पहले मुझे, ऐसा. So FCFS means first come first serve, right? Then SSTF means shortest seek time first, right? SSTF means shortest seek time first, shortest seek time first. So we are only considering the nearby request, right? Nearby request for to get us shortest seek, right? Shortest seek. Then we have four types: scan, C-scan, look, and C-look. Okay, there is a doubt. Let's search cylinder equal to tag. What is the meaning of that point? Cylinder equal to set of tags at same radius of on all the surfaces. And we have already discussed this thing. See here, cylinder will be same radius across all the surfaces. So I think I have wrote it two times. Right? Maybe you can remove it. Right? Below point. Okay, so seek time will be movement between the cylinders, not the tracks. Okay, so yeah, what is the seek time? What is the seek time? So if you look here, if you look here, so it's like you have to move between the cylinder, right? See, this is the reader head only. This is the reader head only. Reader head will have to select one particular tag head. It have to select one particular tag. So maybe yeah, maybe if you confuse, you can remove this, yeah? Movement between the cylinder, yeah. Okay, if you confuse, you can remove that point. Yeah. So now see this. I hope the picture is visible. Right? I hope the picture is visible. A similar picture we have seen. So we have three types like scan, C scan, look, and C look. So what the scan will do? If this is our direction, if this is our direction, right? So the scan will go in this direction first, right? Then it will go till the end, right? It will go till the end, then it will come back and solve, and then it will change the direction. Yes, yeah. Scan go till the end, but so here, see here it and scan goes till the end. Now, what is the optimized version of scan? Optimized version of scan. Maybe I can add here. Optimized version of scan is look, and optimized version of scan is clook. C scan is clook, right? So now if you see here, if you look into look, okay, look into look, look into look algorithm. Yes, look into look algorithm. So see, look here. So if this is the movement, so we are not doing this extra thing to go till the end, right? So in the look it goes till the required is present in the direction. So we are not going till the end, right? In the look we are not going till the end, but here itself, if this is the last request, we change the direction, right? We change the movement of our request. Yes. So that is the look. It will go till the last request. Yes. Now, what is the C scan? What is the C scan? If this is the like desired diagram, like desired location to go movement. Sorry, movement. So in the C scan, see you see the red color, right? Maybe okay, where is the here? Here everywhere. Okay, here look into this red color, right? Look into red color only in this way. Okay, only in this moment your request will be solved. Okay, your request will be proceed. So only in the red color, see, in the red color only it will be proceed, right? It will be proceed, but it will go till the end, right? Because it is scan, right? See, it is circular scan. C means it is circular, right? Because it is scan, so it will go till the end, right? It goes till the end, right? So one side you will solve, yes, one side you will solve, but other side, right, in this direction you won't solve. You solve in this direction, but this direction you won't solve, right? Now what is the optimized version of C scan? C look, right? C look. So see this red color, in the red color, if this is your direction, right, it won't go till the end because it is look, right? Look won't go till the end. So it won't go till the end. Right? And see here, it proceed only in this direction, right? So see this red color. See this red color. It proceed only in this direction. Clear? Clear this point? Yes or no? So these are the four types, right? And many PYQs, like many recent PYQs also are present. So please solve the PYQs if you haven't, right? Many PYQs are coming now with the disk scheduling topic, like algorithms. So with that, I think we stop now, or should we take this floating point? Yeah, we can take the floating point. We can take the floating point. It's normal. It's somewhat less. And then we'll stop with the floating point, and then we'll discuss further after in the next lecture. Okay. So then after the disk, we have seen in detail the floating point representation. Right? Floating point representation. So the entire floating point representation, so the number is represented in this form like S, E, and M, right? So S means sign, right? E means exponent, and M means mantissa, right? So S is for sign, either it is positive or negative, right? So either it is 0 or 1, right? Either it is 0 or 1. Then exponent is biased, right? Exponent is biased. So we are storing here biased exponent, yes, biased exponent. And mantissa is normalized, and this bit represents how many bits after dot, right? So if you have wait. Yeah. So if you have something like 2.3335 and all, so after the point, this will be your mantissa, right? This will be your mantissa, and this entire things will be stored here, right, in the mantissa bits. Yes. So tell me, if you have more bits in exponent, what you will get? You will get the larger range, right? Larger range. And if you get more bits in mantissa, what you will get? If you have more bits in mantissa, what you will get? If you have more bits, then you will get greater precision, right? Greater precision and accuracy. Because after the dot, if you have many bits, right? After the dot, if you have many bits, then greater precision or accuracy you will get. Yes. So that's the thing. If you have more bits, okay. Now see, what is your actual exponent? It is the stored exponent minus bias, right? Stored exponent minus bias. So we are storing here biased exponent, right? We are storing here biased exponent. We are storing biased exponent. Yes or no? We have seen it. We have seen it that we have seen in detail why we are storing the biased exponent in our lectures. Biased exponent. So we if we have to get the actual data, if you have to actual data, then you have to subtract with the bias, right? You have to subtract minus bias to get it, right? Minus bias to get it. So if bias is not given, so if this is okay, okay. See, if this is the exponent e, right? If this is the exponent e, and if the stored exponent is small e, what is the small e? E is capital E minus bias, right? And what is the stored exponent? E will be stored plus bias, right? You are adding the bias into it. You are adding the bias into stored exponent. Yeah, like this. If this is the actual exponent, right? If this is the actual exponent, you are adding the bias. You are adding the bias. Yes or no? Yeah. So now if the bias is not given, bias if not given can be calculated as 2 power k minus 1. Minus 1, right? 2 power k minus 1 minus 1. So if k is the number of bits, exponent bit. Okay. If k is your number of exponent bits, so 2 power k minus 1 minus 1. Right? Now, by default, we are using explicit normalization if nothing is given in the question. Okay, if nothing is given in the question, explicit normalization. So minus 1 power s into 0 point m into what is the explicit normalization? 0 point m, right? And what is the implicit normalization? 1 point m, right? And explicit, there is one thing after the 0, there must be, after the point there must be 1, right? Like after the dot there must be 1. Yes, in the explicit normalization. And this is the value formula. So currently we are looking into conventional, right? Conventional representation. Conventional representation. So in the conventional representation, what we can't do, we can't store 0 and very small numbers, right? We can't store this 0 and very small number. Like if you have See, look into here. So this is the underflow, this is the underflow, like very small number, and this is the outer flow, right? Overflow, right? Overflow. Like smallest negative, smallest positive, largest positive, we can't store it. So the same thing, we can't store zero, and very small numbers, overflow and underflow, we can't store. So now then comes IEEE 754 representation. Okay, to solve that particular issue. Okay, to solve conventional representation, there comes IEEE 754 representation. So it is divided into two, single precision and double precision. This is most important, right? Many PYQs, many PYQs are there. Single precision with 32 bits, double precision 64 bits. So this you have to remember, right? I have told you that sine is 1 bit, exponent 8 bits, and mantissa is 23 bits, 1, 8, and 23. And your bias will be 2 power 8 minus 1 minus 1. So it will be 127. At 127. So bias is 127. So here the bias formula, okay, here the bias formula will be 2 power 8 minus 1 minus 1, right? Yeah, I think in the conventional representation, right? Here in the conventional, you don't have to do minus 1. Right? We have seen. Here, I think you don't have to do minus 1, right? This is in the conventional representation, okay? In the conventional representation, right? You don't have to do minus 1. You don't have to do minus 1. Right? Now here, by default, IEEE 754 uses implicit normalization. Okay, implicit normalization it uses. Implicit normalization, which means 1 point m, right? 1 point m. And yeah, this is about the double precision, like 64 bits, 1 bit for sine, 11 bits for exponent. Mantissa will have 52 bits. Bias will be 2 power 11 minus 1, so 1023. Yes? I think this is not that much important, like double precision, but we don't know. Let's say in the GATE 2027 exam, it may come. How? Okay, you have to prepare for the worst. You have to prepare for the worst. Anything can come. Till now, there is, I think, till now there is no PYQ of double precision, but we don't know the GATE professors, like IIT professors. They can change their mind anytime, right? They can change their mind anytime. Yeah. Now we have seen something called as denormalized, right? So this you have to remember for single precision and double precision, like denormalized values, right? Denormalized value will be this much. Okay. You can't represent beyond this. Okay. Minus 127, minus 126. You can't represent. Okay. You can't represent in this. Okay, you can't represent with the help of normalized number, so that's why you are using denormalized. Okay, that's why you are using denormalized for the, okay, for the normalization you can't represent beyond it. And we have seen one proof also in our lectures. We have seen one proof also, right? One proof we have taken one example, and we have seen that if you do with the help of IEEE 754 representation, and you can't do it, right? You can't do it. So now, so now this table I told you to remember. Okay, I told you to stick in your study table and see the table every day. Look this table every day so that each fields will be clear. Okay. So this is the IEEE 754 table only, right? Table only. So here, see how to represent plus zero. Okay, plus zero. So plus zero. So if you have sine zero and exponent will be all zeros, mantissa will be all zeros, right? So these are the special numbers. See, positive zeros, then negative zero, positive infinity, negative infinity. These are the special numbers. So their representation, right? Their representation is fixed. Okay. So the representation is fixed. Now, if you want to represent minus 0, what you have to do? Just change the sign bit, right? Just change the sign bit. Now, if you represent plus infinity, right? Positive infinity. So sign will be 0 because it is plus. Then exponent will be all ones, mantissa will be all zeros. If you represent negative infinity, just change the sign bit, right? Just change the sign bit. Now, if you want to represent not a number, okay, if it is either invalid or indeterminate, then sign can be either 0, 1, exponent will be all ones, mantissa will be any non-zero, right? Any non-zero. And then comes the denormalized number, it very small magnitude, right? In that also sign will be 0 or 1, exponent will be all zeros, and mantissa can be anything, right? Any non-zero. And see the last field, that the normalized number, this is implicitly normalized, right? Implicitly normalized, and you can take only sign equal to 0 or 1, you, right? And your exponent can't be all zeros and can't be all ones. Why? Because it is used for these purposes, right? Because it is used for these purposes. So exponent can't be all zeros and all ones, and mantissa can be any value, right? Mantissa can be any value. And with the help of this thing, we have seen largest value. We have calculated largest value, right? We have calculated what the smallest value will be. Yes or no? And their latest PYQs like 2026, 2020, yeah, 2026 PYQ also is there with this particular field. Okay, and we have seen that why denormalized will be denormalized number we can take, because there is a constraint of the normalized number till minus 126 only it can able to store. Okay, and here in the double precision minus 1022, beyond that it won't store. So that's why here comes the denormalized number, it is used for very small magnitude, very small magnitude. Got it? Got it, this table? So this table is very important. Okay, so yeah, I think now, yeah, from tomorrow we will see the cache organization, right? And then we see pipeline, and then we see control unit and all, right? And with that our short notes will be over. So today we have seen IEEE, we have seen floating point, we have seen representation, disk we have seen, risk versus risk, addressing modes, instructions and addressing modes, right? Then we have seen memory organization, and we have seen some prerequisite and some of the type of CPU registers and all. So yeah, so with that, I am ending now. Okay, and tomorrow with the same timing we will continue further. Okay, we will continue further. So with that, thanks for joining, and we'll be continue tomorrow. Yeah, thank you. Bye bye. Good night. Keep on revising. Okay, keep on revising. I hope you don't forget my special dialogue to